It's my pleasure to talk to you this afternoon about one of our research projects that we're carrying out in our office in Dublin. What struck me when listening to the talks over the last few days that we do a very different approach. Most of the talks that I've heard really try to get more out of a commodity platform. We do the opposite. We say, okay, let's do, my mom would call that tabula rasa. It's clean slate, whatever you do. So let's actually come up with the perfect architecture to map your application. And that's what we've done. So to be specific, we've explored the use of Dataflow Architectures for the implementation of key value stores, Memcached to be precise. And our prototype can demonstrate that with that, there's no problem on achieving 10 gigabit per second line rate, and that's just the start. Before I get into it, I have to say this is a collaboration between Xilinx Research and the ETH Zürich, and both my co-authors, Kees Vissers and Zsolt István, are in the audience if you have questions later on. Okay, so key value stores, as all of you know, are a common middleware application running on x86s to alleviate access loads on databases. But you know all of that, and what we're going to do during the talk, we first review state-of-the-art. So what do the typical implementations look like, and what's the performance that you can extract from them? The second bit that I'm going to talk about is I'm just going to very briefly introduce FPGAs to you. I think most of you have probably heard at some stage in your life about FPGAs, so I'm just going to do a very small refresher so you can follow the rest of the presentation. And then we're going to deep dive into what's really interesting, into the architecture that we're proposing here, and then finishing up with the results and the limitations. So that's the plan. So let's take a look at the state-of-the-art. Typical Memcached applications are implemented on x86 servers, right? So you have a motherboard with an x86 and stuffed with as much DRAM as you can cram in the box. And then you have a network adapter sitting somewhere in a PCI Express slot, which has a 10 gig interface, or maybe even still a 1 gig interface, and some sort of network controller ASIC sitting on it. The best numbers that we have found, and there is a fluctuation because since we're doing this since a bit more over a year, the numbers are creeping up as well. The best number that we found so far was published at the end of last year by Intel, and that is the second one from the top. It is implemented on a dual socket Xeon implementation and yields 3.15 million requests per second. So it's the best number. Now, if you want to compare that to one FPGA implementation, that's not a fair comparison, right? Because it's two chips. So what we have to do is we have to take the number for the single CPU. So we take the other number that's from the same publication for one Xeon processor, and that's at 1.34 million requests per second. Average latency that we're going to take is somewhere 200 to 300 microseconds, and your power efficiency is going to be something in the range of 7,000 transactions per second per watt. So that's what we're going to compare to. So here comes the tangent. Just briefly, quick refresh, what are FPGAs? So FPGAs are semiconductors. I would call them the chameleon under the semiconductors because they can basically become any device that you want them to be. They consist of a sea of configurable logical blocks connected via programmable interconnect. And you have that pretty picture there. That's not quite accurate. In reality, it looks more like this. It's integrated on an extremely large scale, right? So you can have 2 million logic cells in the current generation, and they are integrated on a 28 nanometer process. Nowadays, also, there is lots of other stuff inside them. You have embedded SRAM, DSP slices, high-speed serial I/O, and even ARM processors. So they become much more system on chips than they have been in the past. But the fact here is you can turn the FPGA into almost any circuit that you want it to be, and that's exactly why we use them to explore data flow architectures for Memcached or key value stores apart from the fact that I'm working for Xilinx, of course. Now, the other thing that we have to touch on in regards to FPGAs, and that's all I'm going to say about FPGAs, is how you program them. And that's important to understand because that is the key drawback that you're going to get with the FPGA implementation. You get a massive performance boost, but it comes at a cost, and that's the design cost, right? So just to quickly revisit this, as said, you use FPGAs for creating hardware designs, which really means, in essence, that you have to describe them through a hardware description language. You have to go through a loop of simulations until you achieve functional correctness, and then you push them through the physical tools, so synthesis and place and routes. And again, you might have to go through a number of iterations here because you need to meet your physical design constraints. And out pops your executable, or the bit stream in FPGA speak, with which you can program the FPGA. Now, so there's much more complexity exposed to the end user in order to create this design, and hence there is much more development effort required to program these designs. That's the cost that comes with it. To lower this cost, we're working actively on high-level synthesis tools, which basically raise the abstraction level in the design entry, provide you with a programming environment in C, which then from there synthesizes down into the hardware description world. Okay, so that's enough about FPGAs. That should be sufficient to follow the rest of the presentation. So let's talk about the architectures. So many of you might wonder, why did you come up with a Dataflow architecture for Memcached? And here's why. Because to us, fundamentally, Memcached is a streaming problem, right? You have the data on the network, and you move the data from there into DRAM, and then you move it back. It's a streaming problem. And on the way, what you do is you receive the packet, you parse the packet, you hash the key, you access the value store, potentially read a value or write a value, you format a new packet, and you send it back out. And that's a very typical streaming type of application. And Dataflow architectures that we know very well from the networking context are very well suited for this. So that's why we said, okay, let's see what a Dataflow architecture can actually do within this application context. So this is the system level architecture. So at the very top, we use a server, right, with x86 and DRAM, but they basically don't do anything. They have very little functionality, and I'll touch later on what exactly is running on that box. The Memcached implementation and the network stack completely reside within the FPGA, which sits on the network adapter. So you have on the network adapter now the 10 gig interface, the FPGA instead of your network controller, and a whole lot of DRAM, where your hash table and your value store are going to reside. And there's a number of things that you're going to gain from this. So you're going to get the high throughput because we're using a Dataflow architecture, and we'll go through that in detail on the next slide. You also get a really low latency, because now when you look at the diagram, the network, the compute, and the memory are completely tightly integrated, right? Not like on your standard architecture where you have to take your data and DMA it over the PCI Express bus, compute, and then DMA it back. Everything sits really close together. And the prototype that we put together is designed to actually contain a hash table that can hold 2 million entries and address a value store of 24 gigabytes. So, and this is probably the most important slide of the entire presentation. This actually shows what our Dataflow architecture looked like. And in order to get across how this thing works, I've animated it with the so-called life of a packet, right? So you have the packet coming in from the network. So everything in the gray box is contained within the FPGA. And the first unit that it hits is, oh, you can't see the FPGA boundary, can you? Yeah. It's everything between here and here, right? So we're now inside the FPGA. The FPGA holds the UDP TCP offload engine, which handles the complete TCP IP stack, right? And it strips off Ethernet, IP, TCP, and UDP header, stores whatever is necessary, and then only sends the Memcached part of the packet on, and that goes to the request parser. The request parser is responsible for handling the Memcached protocol, so it understands currently ASCII and binary. We've built both of those. You could add many more to it. The request parser is supposed to shield the rest of the processing from the different formats of incoming requests. So what it does, it normalizes the request onto an internal standardized format. So it extracts the key, it extracts the value if it's present, and extracts all the metadata. So how long is your key, how long is your value, what type of operation do I have to code up, and during the processing stage gets added to the metadata as well. And that's then conveyed to the next pipeline stages over a fully flow-controlled streaming interface. So request parser normalizes the packet and forwards it on to the hash table. So the hash table takes the key and computes the Bob Jenkins lookup free hash function over it, and that produces then the index into the hash table. We do the lookup in the hash table, which returns the address to the value store. That gets put into the metadata information and then passed to the value store. The value store takes the address, does a lookup in DRAM, retrieves the value. Now this is for a get operation. For a set operation, the exact inverse would happen. And then the packet is forwarded to the response formatter, which creates out of this a valid Memcached response. And that goes back to the UDP TCP offload engine and from out there to the network. So that's basically how the packets are being handled inside the Dataflow architecture. So first of all, I want to give you an idea of the complexity of this thing. So we use, to code this one up, just the Memcached pipeline, 16,000 lines of code. The Memcached code base has 10,000 lines of code. So we're a little bit more, but it's not outrageous. There will be more in the future because we are limited with the functionality that we are, but it should give you an order of magnitude on how complex that code is. The second thing is that the entire pipeline inside the FPGA handles one packet in 481 cycles. So there's 481 cycles from when the first byte comes into the FPGA until it leaves the FPGA again. And that's clocked at 156 megahertz. So if you compare that now to your x86 implementation, the x86 takes 1 million cycles at 2 gigahertz. So you can inherently see where the latency bandwidth benefit is coming from. So 481 cycles. The second part that you're going to get is, you can really see from this already, it's going to be much more power efficient, right? You're only clocking 481 times until that packet is back out again. Then you're going to get the really high throughput through exploitation of task and instruction level parallelism, because there is not one packet going through the pipeline. There can be up to 23 packets concurrently residing in that pipeline. So while one is sitting in the response formatters, there might be 3 sitting in the hash table and another one in the value store, right? So this is all operated in parallel. The hash table architecture itself is part of a different publication, but just to get the basics right, it's a Bob Jenkins lookup free that's implemented in the FPGA. We do collision handling up to a level of a bucket size of 8 through a parallel lookup, and we do handle flexible key by striping them over multiple memory locations. But again, there's more detail in a new publication. This one here is about the Dataflow architecture. On the system level, you can see on the left-hand side the network adapter with the FPGA board. On the motherboard now, so that's the x86 but the DRAM, what's running there in regards to Memcached is only the memory allocation. And we had to move that onto a different chip because we ran out of memory I/O bandwidth on our specific platform. On other platforms, it could have gone on the FPGA, not on this one. And the only other thing that runs on the x86 is the configuration of the FPGA. So you program the FPGA from that x86 and you can control it, for example, setting up IP addresses and such. But that's all it is. And it's extremely lightweight. That's like, I put it down on the note, less than 3% of one of the cores on the x86. So this is how we tested our system. We first installed 2 servers with the Memcached software, the open source distribution, and the Memcached test clients, MEMSLab, MCASLab, and all the other ones, and we reproduced the performance results. Then we built up a Memcached server and checked that our appliance is actually functionally compatible with the existing infrastructure. Then, because these x86-based test clients are nowhere fast enough to performance test our FPGA appliance, we purchased a network tester that can really blast the packets at our FPGA implementation, and we used a handcrafted FPGA design to measure latency really accurately down to the cycle. And this is what it looks like in the lab, right? This is, but only when it's really tidied up and cleaned up and all the coffee mugs are removed. So you have the servers on the right-hand side. In the middle, the net FPGA board that we use for latency measurements. There behind the laptop is our Memcached server hiding. It's a Maxler workstation with a FPGA adapter inside, and we test with 10 gig interface pin. And the Spirent test center is photoshopped in there. I didn't clean up twice. So this is how we measured power. To put it simply, we just put a power meter at the wall plug on the test system. When you look on the left-hand side, it's right here, and then we did little experiments where we measured the host system without the network adapter and then with the network adapter, and then we correlated it with data sheets and power estimation tools and regulator readings. Okay, and now we're coming to the performance. So what you can see here on the red line, visualize the performance of the FPGA, and it is measured over packet size, right? They go from 96 bytes to 1090. And you have on the y-axis the number of responses per second that the Memcached server can handle. So we can handle the absolute maximum performance that's available over the network. So that's around 13 million requests per second. And that degrades with the packet size because that's what happens on a 10 gig link, right? That's actually the theoretical maximum that you can get on a 10 gig line. The larger the packet, the smaller the packet rate is going to be. That's why it declines. The x86, that's from the Intel paper, hovers around 1.34 million requests per second, and that is a relatively stable number because the performance of the x86 is dominated by the per packet processing overhead, so it's almost independent of the size of the packet. And that continues and with even when packets get larger and larger until you eventually hit the limit from where even the x86 will keep up with the 10 gig line rate. And then it declines from there. Okay, so that's the performance. So as you can see from this, sustained line rate processing is possible with up to 13 million requests per second, which is a significant improvement over the x86 number, if I remind you. Where's my mouse? 1.34 million for the x86. That we're down here with 13.02. The second aspect is that we are lower in power, and again, that shouldn't come as a surprise after you've seen the architecture slide. To be a little bit more precise, the FPGA subsystem on its own consumes around 50 watts with very little variation. There's about 2 watts variation depending on how many gigabits per second of traffic you're pumping through. So it's between 49 and 51. And when you look at the breakdown of the power consumption, the FPGA on its own is 15 watts. The majority is 24 watts is from the DRAM subsystem that sits on the FPGA adapter, right? So the black bit is the FPGA, this is the DRAM, and the rest are the 10 gig interfaces, the loss in the regulators, etc. So if you combine those numbers with each other, right, we're going to get 254.8 thousand requests per second per watt that we can handle in comparison to the 7,000 that the x86 can do. Now you might say, okay, but we don't have all the functionality and there's something running on the server. So even though it's less than 3% on one core. So let's take the host system into account, which brings the power consumption of our box up to 120 watts. And then you still would be sitting at 106.7 thousand requests per second per watt that you can handle. And that is, by a long stretch, not an optimized host system for our problem at here. You'd better be off probably with a small ARM processor. Okay, and the last number that we haven't discussed yet is the latency. So your typical x86 would operate with 200 to 300 microsecond latency. The FPGA will give you a reply within 3.4 to 4.5 microseconds. So there's an improvement by 2 orders of magnitudes simply through the tight integration of all the resources within one board. So now all of those good news come at a cost, and in our opinion, the biggest cost here is the NRE associated with actually developing this design. So I've tried to visualize that in a graph. This is not accurate. This is qualitative only. So you have on the x-axis the amount of development effort, y-axis performance, and with an x86, right, you get your design working very quickly, but the performance might not be so hectic. And then you go through an optimization, so your blow line goes up, right? But you are going to hit in the inherent bottlenecks in the architecture, and you can't get beyond that. Whereas with the FPGA implementation, you design the perfect architecture for your problem, right? So you get the performance of the red box, like way up there on the right-hand side, but you need significant more development effort. And so what we're trying to do is, with our work on the high-level synthesis effort, trying to reduce the cost. So that's the yellow arrow. So we're actually coding up our Memcached prototype with high-level synthesis as we speak, to see how much can we bring that line in. So how much, where does the yellow triangle go? The other big limitation that is important to know is TCP offload. So we have a complete TCP IP stack inside the FPGA. Piece of third-party IP is restricted to 64 sessions, which is not sufficient, right, for typical use cases. So we're working on coming up with new architectures for TCP offload. We're exploring extending the storage capacity by using SSDs directly in combination with the FPGA. Next year, I want to come back with an 80 gig appliance and 5 to 10 terabytes of storage, I hope, if it works. And our memory allocation and cache managements are basic. It's a prototype. And we have limited protocol support. So we have set, get, delete, and flush. The other commands are variations of those, but they're yet to be implemented. Okay, so that's me. So in summary, what we show here is that with Dataflow Architectures, you can deliver 10 gig line rate performance for key value stores and provide scalability to higher rates. This is just the beginning. We can go with the same architecture to 40 gig or 80 gig. We can achieve significantly higher power efficiency, and we can reduce latency to a few microseconds. The next steps for us are addressing these limitations that I've just mentioned on the previous slide. And what we're really keen now is on exploring this prototype with real use cases. We're working on synthetic use cases, which to many is not sufficient. So we want to work with real use cases, and we're also interested in learning about other applications. So talk to us about other applications. We're really keen on exploring about what we can do with customized architectures and memory architectures for other applications. Okay, so thank you very much for your attention.
How much would a faster network help?
On our board?
Well, I mean, yeah, your board has the limitation of the tap, but I mean, if you could improve that.
Yeah.
Because I mean, the FPGA has sort of a limited speed, but the question is, how close are you to that?
Okay, so let me be precise on this. So the current implementation operates on a 64-bit data path at 156 megahertz. So we use the same architecture for networking applications where we scale to 256-bit data paths. We even go with some of them to 512-bit data paths. So that gives you, 40 gig to 80 gig path. On top of that, you can increase the clock speed. 156 megahertz is actually very slow for current device generations. So I would say I am using FPGAs since all my life. You can from a processing point of view, you can get to 80 gig, no problem. I don't see any stumbling block. Where you're going to stumble is the I/O pins, right? There's only so much memory you can attach given a number of I/O pins, and then SSD gets really interesting. Right, because SSD you can attach half a terabyte with 2 pins, not like DRAM where you need 170 pins for 8 gig or whatever it is.
Hello, Malte Schwarzkopf from Cambridge. This is nice work. However, there did seem to be an implication that that I thought I'd follow up, which was that you can achieve line rate, which is great, and you can achieve low latency and high power efficiency using FPGAs. But the implication seemed to be you cannot do this using software. And this is certainly true for Memcached, as you can download it from GitHub and run it today. Yeah. But my question is, do you think it's fundamentally impossible to do it in software? And if so, why? Because having looked at the Memcached code base, I know that at least the open source version is not particularly optimized. There's a couple of things like
you can't use the open source software version and translate it into an FPGA. It's a p-threaded architecture, but you can. And that's what we're doing with our high-level synthesis effort. So you have to fundamentally transform the problem into a data flow pipeline, and then you can describe it with the C-based design flow. So
absolutely, I'm not disagreeing with that. I'm just saying, do you think there are fundamental reasons why improving the software implementation an improved software implementation couldn't achieve line rate?
There are fundamental limitations. Now, there's quite a lot of publications on the problems on x86 and why they don't scale for Memcached applications. There's problems with the TCP/IP stack. It's inherently a high interrupt rate, which is causing starvation on your instruction cache. You have the random access nature of the memory access, which makes your L3 cache basically ineffective. There's a whole number of reasons why Memcached doesn't use the x86 to its best performance. That's not we did a little bit of reading and a little bit of software profiling, but as we understand, there are fundamental flaws with the x86 architecture for this application context. However, there are other architectures coming out that have been proposed for this.
Okay, thank you.